Hey, this is Steven from the Green Engineers, and I had a question asked of me on Dave Hackins about why we were looking at a specific area of cross section for basically shearing plastics. So shearing is a plastic deformation of any material, in which case two somethings are basically two forces are counteracting each other. So there are two different types of I guess that this could happen. Obviously, one is tension, and tension is a different type of failure. That's tensile strength. And then you have compression. And then in this case, we have compression of which the planes are both in line with each other. And of course, the better they are aligned with each other, the higher the stress is. So if you notice here this is my design of the shredder, not Dave Hackins' design. And I've removed the front and back bracket, and also the gears, so we could better see this. But these are basically perfectly aligned. And so pretty much we have a force coming from this direction and a force coming from this direction. And here's the gentleman that is asking the question, I believe, right? Yeah, he's the one asking the question, and he has a good picture here. I'm not a very good drawer. This is probably as good as I'd be able to draw. So the force is coming here, and then here, and then here, and then there's another one here, here. So as you see, the forces are equal and opposite in direction. So this way and this way, because this plastic bottle is going to sit there and not move. So here and here are going to be equal. Force is mass times acceleration. If the body is not moving, thus there is no velocity or exchange. When you push on something and it doesn't move, for example, here I'm pushing on the table and it doesn't move, that must mean that because I'm applying a force, which is mass times acceleration, that must mean that there is also, in the other part of the equation, some sort of force that's pushing back at the same magnitude as I am pushing. That is what equilibrium is, as retained to forces. But also something can not change direction if it's already in motion. But in this case, we're talking about something that is not in motion. And when these two blades come up and meet this plastic bottle at the same period of time, the plastic bottle doesn't move. That must mean that these two are applying equal but opposite forces, because there's a force coming from this vector. Vector is magnitude plus direction. So there's a force magnitude plus, and magnitude is value, so what the actual force is. And then there's a direction in XYZ, or a 3D vector, right? So coming this way, there has to be something coming back the other way in the exact same vector and the exact same magnitude that will cause this plastic water ball to not move, right? And then on and on and on down. So on my particular design, it doesn't show it in this model, but I only have one set of blades that are contacting at one time. Only two sets of blades contact at one time. And then the next two contact, That is to bring down the force required, because my initial design is for hand cranking. So here we can see here that the equation is force times area. So really what we're going to pay attention on is the cross-sectional area of material with area perpendicular to the applied force vector, right? I don't know why it says perpendicular. It's supposed to be parallel, but because pretty much it's parallel with the force that is being applied. So basically what that looks like is, this is why I was saying that it should be estimated by a triangular shape. So let's say that we're in Fusion here and we create a sketch here. So let's project this, let's project this, let's project this, and let's project this. So the actual, in this current configuration here, the maximum theoretical size that could fit in here, I estimate with a triangle. Right? See the triangle? That is why I am estimating it with a triangle. Right? Is because this goes in there kind of like a triangle. Right? So that is the reason why I am estimating it with a triangle, is because it's the easiest way to estimate something mathematically by hand. You can see that there is a triangle that will fit in there perfectly. Of course, in this case, this triangle would probably have this actually be like this in actuality. Anyways, we leave that there. Like this. But you get the idea. So that would be the maximum area. And then if we hit measure and we look here, we can see this is the area of cross-section that is parallel with these two things. And so that's why I'm saying a triangle. But in actuality, the maximum theoretical would be, you know, pretty much this. I'll show you guys. I mean, this is the maximum theoretical, is that if we take these and we draw a line here at the top from this point to this point, I mean, that is the maximum theoretical there, the highlighted. But you could see that it would be very, very hard to have a piece of plastic that is in that shape. Probably the closest thing that you'll have is either a square or some sort of rectangle or a triangle. That's why I'm saying a triangle, upside down triangle that goes from here down up. But this is the maximum theoretical. But of course, finding a piece of plastic that big is highly unlikely. So this is 1.953 inch squared. Now, the reason why we are using the what's parallel is because when these blades come here, what you have to think of is what is in between the two forces. The piece that is in between the two forces is this geometry. So pretty much how things are held together in the world in solids is that there are bonds, right? There are molecular bonds with all the molecules that are inside steel or plastic or liquids, you know, water or hydrogen bonds, blah, blah, right? In this case, you know, carbon bonds, iron bonds, stuff like that are bonding these, that create this crystalline structure inside this material. Or you have either organic or inorganic bonds that are holding together the plastics, the different carbon-based plastics. Now, that is the material that is in between these two forces here. And of course, the force is actually coming around and chopping through. And so pretty much what you have to look at is if you took a cut of this piece, what would be resisting these blades? This piece right here would be resisting these blades, this material here. And that is a slice. If you took a slice of it, that is the bonds that are preventing these blades from turning. And in order to shear through, we're going to have to break those bonds and basically, like you see in that game, what was that one? Fruit Ninja, where you cut right through the watermelon, the two pieces just come off. So instead of thinking that this guy is actually taking a bite through here, think of it as if it's going to break the piece and the two pieces are just going to slide off the table. For example, think of a knife, how it's super thin, and it goes right through the material, and it just slices the two pieces of material right in half. And let's say you have one piece on the table. Let's say you have one part of the watermelon sitting on the table, and the other half is over the edge of the table. And you cut it, the other piece of watermelon just falls right out. Right? So same deal here. Basically what it's doing is this blade is pushing this way, and this blade is pushing that way. And it just cracks the material and pushes the two into their respective holes. So the reason why a blade is so thin, why like a samurai blade is so thin, is because it has these two relief angles that help give the material some place to go, some place to separate, right? And in the case of a samurai sword, the reason why there's only one blade and you can still cut is that, just like I said about the table, there's something else in there in that environment that is holding the material back up towards the blade in an equal and opposite direction, so that when the blade hits something and it doesn't move, there is an equal and opposite force to that material. But in our case, we don't need that recess to split the material, to open the material up. Because another thing is also, as the blade's coming through, we don't want to have a whole lot of friction, right? And what happens is, if you have a blade like this, as it's going through the material, there is going to be some friction where it's rubbing against the part that you just cut, right? In the case of a samurai blade, when you go down, as it goes into the material, it's starting to split the material open, and that's also that's putting the material also in a tensile pull to open it up, and it's moving the two pieces of material away from each other, so that also that lowers friction. But in this case, when we split the material, these blades come down next, so we have this opening that we're pushing our material in that is about the same size as the blade. So this blade pushes material in here, this blade pushes material in here, this blade pushes material in here, this blade. So we have a dedicated section for all the material to go. But obviously it can possibly get stuck, but the blade's going to keep pushing it down and pop it out the other end. It could get stuck on the blade, but that's why we have these here, so that as it comes around the bottom, it gets knocked off by these pieces here. So that is basically the gist of here the shear. And the reason why shear is about the general rule of thumb is shear is about 80% of the tensile strength, because we have such concentrated forces on two opposite ends. And all this, there is a different equation if these are split. So if these are further away, then the equation is way different. But if they are nearly in line here, so we could treat as if the forces were on this edge and the other forces were on this edge, that they are pretty much, the forces are almost right on top of each other, but opposite in direction. And that is what heightens our forces. Heightens our shear stress. So let's say that we had this, let's say that we deleted this blade and this blade, and we had this blade and this blade. So forget about these two. Now this is so far away that pretty much it's just, this is pushing the material down and this is pushing the material down the other way. So basically it's just going to try to twist the material apart. You don't have a very good focus on a knife's edge. That's why they call it on a knife's edge of forces. That it's going to take a massive amount of force to push it through. And that's also another reason why our blades don't necessarily have to be sharp, because all it has to do is that this face has to be parallel here, as parallel as possible. And actually it doesn't even need to be that. It's just that it has to be that this edge, you could even have it to where this edge engages, and then this edge is actually kind of recessed, where it goes like this. And even that will work. So this one is like this, and this one is like this, right? All you want to do is you want to have a nice point instead of a rounded edge. You want a nice sharp edge at this to concentrate all that stress on the material, right? And when you move it through, it will separate. It'll, I guess you could say, part, kind of like on a lathe, where it just comes in and it just, you can imagine that it just basically rips the material off. It doesn't cut the material. It just it puts so much force on the material that the force can the internal forces of the material that hold the material together can no longer counteract that, and it just starts to move, right? And so there's internal shear stress, which basically is what what happens here. And then there is, inside the material, there are these fractures inside the crystalline structure that propagate, and it goes down through there and basically breaks the bonds that are holding the material together, and then it just eventually breaks free, and the two materials, the one material now becomes two materials, because it's basically been pressed so hard and so much pressure, so much stress on the inside of the material, that now it's just cracked and broken free, and now it's two pieces of material instead of one. So it's not really cutting it per se. I mean, it's basically coming in and putting so much pressure on something that it comes apart, and that it can no longer hold itself together. So hopefully that makes sense. I'll answer more questions as they come available, and I will be updating more Green Engineer stuff soon, and I'm working on getting some of these guys made and shipped. Thank you guys for watching, and I'll see you guys in the next one. Take it easy. Peace.